Hi there, and welcome to section 1.4, where we're going to look at the topic of subspaces of Rn. So in the last video we started, describing Rn as a vector space. And we really didn't get into too much of what that meant. We just saw some of the things we're allowed to do in that vector space, right? How to add and subtract vectors, take scalar multiples. We saw a lot of properties about this sort of mathematics, this vector mathematics in Rn. And here we're going to see that certain subsets of Rn, notice subset and subspace are very different words. It's almost too subtle to be fair here, but we really do have very different meanings between the words subset and subspace. A subset is just any collection of items in Rn. A subspace is a very, very specific type of subset, very specific type of collection of items in Rn, elements in Rn. So we're going to see certain subsets, certain collections of items in Rn, elements in Rn, have the same algebraic properties as Rn itself. What are those? Well, we haven't really talked about what makes a vector space, but that's what we're getting at here. The same things that make Rn a vector space, we'll see certain subsets of Rn have those same properties on them. Any of these subsets that have these special algebraic properties that kind of match up with Rn itself are called subspaces of Rn by definition. That's the definition of a subspace. We haven't really given enough to really know what a subspace is by that definition, but we'll talk about these algebraic properties more to clarify. So it turns out to check that a subset of Rn is a subspace, not just any old subset, a very specific type of subset called a subspace. To check that one is a subspace of Rn, the subset must be closed under addition and scalar multiplication. And we briefly talked about what that meant for Rn as a whole. We said Rn has this property. It's closed under addition and it's closed under scalar multiplication. Now, all that meant for Rn was that if you take a couple of elements, a couple of vectors in Rn, and you add them together, you get something still in Rn. Similar for scalar multiplication. If you take a scalar times any element of Rn, the result is still an element of Rn. That is closure. That's closure under addition and scalar multiplication. It turns out if you define a very specific subset of Rn, not all of Rn, but you restrict and just look at some of it, and you find that that little subset you've defined is also closed under addition and scalar multiplication, that if you take any two elements in there and add them, they're still in that subset, or you take any element in that subset and multiply it by a scalar, and it's still in that subset. If we have that closure property, the subset is called a subspace. So that's important. Closure under addition and scalar multiplication implies we have a subspace. Okay, in Rn, we'll see that in more general vector spaces, we have to be careful. We have to think about whether this fact would still hold more general vector spaces than Rn. We'll see that, yeah, we already mentioned, Rn is a vector space. We mentioned that. We are going to see that there are many other types of vector spaces as well. And we're going to have to consider carefully what all that we've learned about Rn is actually going to transfer over and also apply to those other types of vector spaces. We want to be thinking these things are going to get very kind of abstract, but for now we're just thinking of real space, right? R2, R3, things like that. So if the subset meets these two requirements, is closed under addition and scalar multiplication, it turns out it automatically inherits all the algebraic properties of Rn. Right? We're already saying we're taking a subset of Rn. So this subset that may or may not be a subspace, this subset that we're talking about contains elements only from Rn. So all the properties of addition and scalar multiplication, things like that on Rn still apply in this subset, right? It's in Rn. It just turns out if you get closure under addition and scalar multiplication in your subset, which we'll explore further, then in that case, all those algebraic properties we covered on Rn still apply to that subset. It inherits all those properties. Now let's look at an example here to try to get a better sense of what's happening. Let's consider the set of all vectors of the form a comma b comma 0, where a and b are some real numbers. Is this a subspace of R3? So what we've defined is a subset, right? Not all points in R3 have this form. Not all of them have a 0 in the third component, but certainly a subset of them do. All of them with a 0 in the third component are in this subset. Now we want to know, is that subset really a subspace? Is it closed under addition and scalar multiplication? Meaning if I take two elements of this form, number, 0, when I add those together, is it still of this form, still of the form number, then specifically 0 in the third component? And if I take a scalar multiple, is that scalar multiple still of this form? That would give you closure of this subset under addition and scalar multiplication, which would imply it's a subspace. So if we take this vector a comma b comma 0, notice we can immediately break it up as a comma 0 plus 0 comma b comma 0. If we added those back up under the rules of addition in R3, we'd get what we started with. Well, this is now something we can pull the a out of, right? And kind of reverse scalar multiply that a. Pull that a out, factor it out to the front, so it's a times 1, 0, 0, right? Multiplying that a back through certainly would give me a 0, 0. Do the same thing with the b. Pull the b out and leave 0, 1, 0. And we're kind of seeing something valuable now. We're seeing anything of this form ab comma 0 is really just a linear combination of the vectors 1, 0, 0 and 0, 1, 0. Right? It's some scalar times 1, 0, 0 plus some scalar times 0, 1, 0. So we've really kind of gotten at something more fundamental about this subset. We're saying things of this form are really just things that are linear combinations of 1, 0, 0 and 0, 1, 0. So that's really the subset we've defined. I shouldn't say it's a linear combination. I'm going to say the subset is the set of all linear combinations of this vector and this vector. Now, what does that look like? If we were thinking visually, in three-dimensional space, 1, 0, 0 would say go 1 unit in the x direction. I've kind of drawn that down here. From the origin, go 1 unit in the x direction and 0 in the other directions. So from the origin, I am just looking at, you can draw this vector. And 0, 1, 0 says go nothing in the x, go 1 unit in the y, and nothing in the z. So from the origin, we go 1 unit in the y, nothing else anywhere else. So that blue and red vector I've drawn are these two vectors that anything in our subset is really just a combination of, right? Any other value in here, or any other vector that's in this subset, is really just some parts of this red vector plus some parts of this b vector. For the parts, the amount of each are the a and the b that we're seeing, right? The scalars in that linear combination. So say I did have a times this first vector. Well, that would take me to something like, yeah, let's just say this red vector is really a times. In fact, let me doctor this up a little bit. Let me say this a vector, or this red vector, is shown there in red, blue guy shown there. Well, then if I was to add these, right, see what vector I'm actually talking about in my subset, if I add these together, add this guy plus this guy to see the element I'm really talking about in this set, well, vector addition would give me just, by that parallelogram rule, black pen, it would give me this vector, a times 1, 0, 0 plus b times 0, 1, 0. And notice by the rules of vector addition, that guy is still trapped in this xy plane defined by that red and blue vector. they're given any two vectors, one direction this way and one direction this way, no matter how they're oriented in space, there's always a plane that's defined by those two vectors. So that's what I've sketched out here very lightly, is the plane defined by this 1, 0, 0 and 0, 1, 0. And what we're seeing is that any combination of those still sits in that plane, right? So if we want to figure out, is this set, we've kind of pictured what this set looks like. It's just this plane here. Any linear combination of 1, 0, 0 and 0, 1, 0 will be some vector that lies in this plane. If we want to determine, is this a subspace of R3, what do we have to do? We have to see if this is closed up here, have to see if it's closed under addition and scalar multiplication. If the subset is closed under addition and scalar multiplication, it's really a subspace. So let's see how to do this. I've made that same note over here. Right? It suffices to check that any linear combination of vectors in the subset is still in the subset. Right? That's checking closure under linear combination. Maybe I should clarify that. I said up here that closure under addition and scalar multiplication implies it's a subspace. Here I'm saying closure under linear combination. And that's true because that would require that both scalar multiplication and addition have closure. Well, let's see the little proof I've written out here, just in simpler terms. If U and V are in this subset, then they have this form where you have a number, then a 0. So let's think of two objects of that form. Let's let U be a vector in there that has components U1, U2, then 0. Putting a 0 there ensures it is in the subset. And let V be a vector in that subset with components V1, V2, and 0. Again, the 0 there ensures that we are of this form. Well, then we just check. If I add these two, what do I have? I still have something with the 0 in that last slot. So I still have the correct form. This is still in the subset. If I take a scalar multiple and multiply it through, when it hits that 0 in the last component of U, it just turns into a 0. So still that scalar multiple will have a 0 in the last slot, meaning that this is still of this form. We are still in the subset. So yes, the set of all vectors of this form, it is closed under addition and scalar multiplication. This is showing it's closed under addition. And this shows it's closed under scalar multiplication. Now what I was getting at over here, oh, I should just finish up my thought there. Since it's closed under both of these, the subset of all vectors of the form A, B, 0, where A and B are real numbers, is a subspace because it has closure. We will see not all sets have this property. Plenty of sets are not closed under one or the other or both of addition and scalar multiplication. Now, I want to clarify what I said over here. It suffices to check that the subset is closed under linear combination. Just meaning instead of doing these separately, you can just check. You could check it all at once. You could check that C1 times U plus C2 times V is in the set. That would prove closure under addition and scalar multiplication all at once. That's what I call closure under linear combination. Okay, let's go on from there. We do need to see, right? We need to see what occurs when we are not dealing with something that is a subspace. And even from this picture, I think it's important to latch onto this idea that we've described it a little bit in the last video, that these sorts of subsets we're talking about are typically a point alone, a line, like a set of solutions, a line, or planes, right? Planes we saw could be sets of solutions. Sets of solutions could lie in planes. So when we're talking about these sets, often we're thinking of lines or planes. And I'll just kind of give the game away here. It turns out subspaces are really just lines and planes that go through the origin. That's all you really need, in Rn at least. If you have a line or a plane graph with zero curvature that goes through the origin, you are dealing with a subspace of that bigger space it's in. plane is a subspace of R3, for example. So it's an important thing to remember. We'll see this coming up over and over. I'm even going to make a note. It turns out subspaces of Rn are just lines, I should say points. I'm going to phrase it this way, are lines or planes or higher dimensional planes, like fourth dimensional, third dimensional planes. We can't see those, but they work out mathematically the same. It turns out the subspaces of Rn are lines or planes through the origin. Okay, let's go a little bit further. This is going to be an important idea though, right? Just to kind of jump past building all that intuition to seeing this fact for ourselves. I think this will help guide our intuition from here on out. That when we are talking about subspaces, when I talk about them, I think of a line or a plane through the origin. Even in higher dimensions, when I want to think about how it works in like R4, I'm still just conceptualizing it as a plane through the origin to make it easier to see in my mind. Plenty of analogies follow over from that comparison. Okay, so let's see an example up here. Consider W the subset of R3. W's in R3, right? It's a subset, not an element of, but a subset. Consider W the subset of R3 defined by vectors of this form, a plus 1, square root of b, b. And I haven't written it here, but I'm implying that a and b are real numbers. Any real numbers. If your vector can be written in this form for any number a and b, your vector is in this subset W. Now we're going to ask, is W a subspace of R3? We did the same problem in the last one, except the description here of our subset looked a little simpler. It just was AB comma 0. But we saw that to check to see if this subset is a subspace, we have to check for closure under addition and scalar multiplication. If it fails either of those, it's not a subspace. I think we'll go ahead and check both just to see what happens. So for example, let's take a look here. Let's check closure under addition. Closure under addition. I want to make sure to match something I've written elsewhere. Yeah, so to do this, let's set it up. Let's let U and V be vectors in this subset. So they have to have this form. I'm going to say the form is U1, just some scalar U1 plus 1, root of U2, comma U2. Right, this is the same form as this. Right? When we say a form, we're not concerned with the symbols we're using. We're concerned with the relationship to the other components. Right? Whatever's in the third component, its square root has to be in the second. And whatever's in the first component has to be able to be expressed as some number, some real number plus 1. So we have a real number plus 1, root of U2 and U2. This is the right form, even though we use different symbols. And that's kind of tricky to parse out here, what we mean by the form of one of these vectors. But U is, oops, this is in the subset W. And let's let V be similar. Let's call it V1 plus 1, root V2, V2. Right? These are two vectors, two arbitrary vectors in W. And we have to show that no matter which arbitrary vectors we chose, we are trying to figure out when we add them, do we end up with something that's still in W? So let's add these. U1 plus 1 plus V1 plus 1. That's adding first components. Root U2 plus root V2. That's what we get when we add the second components. And finally, U2 plus V2 is in the third. Now let's check this out. The first stuff we could write as U1 plus V1 plus 2. The next part we could write as U2, root U2 plus root V2. And leaving everything else alone, that's what we have. So is this of the form that we started with? Is this of the form some real number plus 1, square root of some other number, and that number without the square root? Is it of that form? Well, if it was, think about what would have to happen. The number sitting here would have to be inside of a square root here. So do we have the root of what's sitting in the third component in the second component? That's what would be required in order to have it of this form, right? This form says whatever's in the third component, its root must be in the second. Well, we have u2 plus v2 here. The root of u2 plus v2 is not the root of u2 plus the root of v2. No. The root of u2 plus v2 does not equal root of u2 plus root v2. This is not of the correct form. The second and third components don't have the right relationship to each other to be of this form. We have shown adding two things that are in this subset can give you something not in that subset. And you don't want to do this with specific numbers plugged in. Like I don't want to do this with, I don't know, a equals 1, b equals 1, and b equals, maybe b equals 4, for example. I don't want to do that with specific numbers plugged in. You want to always leave this completely general. Don't specify what real numbers you're using for A and B. Call them U1, U2, B1 and B2. What's important is that you leave that general relationship between the components the same, but express it with generality. You don't want to specify the numbers you're using. Right, this shows since we don't have the right second component compared to the third, it says no, this is not closed under addition. And right away we know W is not a subspace of R3 because it's not closed under addition, right? This would be, remember in the last problem when we saw a subset that is a subspace, this plane here, right? In that case, the idea was if you take any two vectors in the plane and add them together, by adding with the parallelogram rule or the triangle rule, you would still end up back in that plane. This is saying that something about this set, as we've described it, is just not of that form. You can take two things that are in this set and somehow leave the set by adding them together. You can't do that with a plane, right? And maybe this is making it make sense why we talk about spaces, why we're referring to these as subspaces, right? In real life, in space as we think of it, if you go any direction, if you have any amount of displacement and you do any other amount of displacement, you're still in this same three-dimensional space, right? We can't escape it by making displacements in 3D space. That's exactly the situation here. You can't escape the plane by making movements that are trapped in the plane, right? That's why we call them spaces. It's like real life, right? Space as we know it and surrounding us always. Okay. So though we already showed that this is not a subspace, right? We already answered this problem. Is it a subspace? No, it's not. But let's go ahead and check scalar multiplication. We already saw it's not closed under addition, but what about scalar multiplication? Let's do this out on the side. Is it closed? Let's see, let's figure this out. Well, the same idea, we want to take an arbitrary element, maybe like C times our U over there, and see what a scalar does when we multiply through. Right? After we multiply that scalar through, we would have C times U1 plus C. We would have C times the square root of U2, and we would have C times U2. Now, we started with a U that was in W. Maybe I write that better. U was in W. And we multiplied it by a scalar C. Is the result in W? Well, what do you think? Let's take a look. The key feature of this subset, W, is that whatever's in the third component, its square root must be in the second. But we have C times U2. Is the square root of C times U2? Is that what we have in the second component? No, right? In general, unless C happens to equal 1, this isn't going to be true. In general, this equation is untrue. So C times U is not in W. It's not of the correct form. The second and third components don't have the right relationship to each other. So we saw this fails to be closed under scalar multiplication either. Before we go on to the last example I had here, I want to move over and actually do another one similar to what we just did. What if we look at letting W be the subset, not necessarily subspace. I'm going to ask if it's a subspace. Let W be the subset of R3 defined by vectors of the form absolute value A. Actually, let's do this. Let's do square root of A square root of B, square root, keep saying square root, absolute value of A, absolute value of B, absolute value of C. So W is the subset of all vectors of this form, where we're just saying every element has to be the absolute value of some real number. And they don't have to be related to each other. Keep in mind, the A, B, and C are unrelated to each other. Whatever A is, B is unrelated to it, C is unrelated to it. There's not a connection between the components like there was in this case, right? The B here had to have its square root in the middle component. Here we're using all different letters, so it doesn't matter what these elements are. All we're saying is each has to be expressible by as the absolute value of some real number. So is this closed under addition? Work that out. Maybe take a break here or pause the video and see if you can work this out. Is this set W, is it closed under addition? How about scalar multiplication? Think this is a good problem to play with? I don't want to give it away though. I want you to play with this a little bit. If you think you got it, or if you're struggling with this, I would really like to see you in office hours. Maybe we can talk about this and work this one out. Go ahead and work on this. See what you can do. Make a note of any question you run into. It might be worth checking your answer, even if you feel comfortable with this. It might produce some unexpected results. I'm not sure. Depends on what you expect, I suppose. But try this problem out. Is this set W, as I've defined it, closed under addition, and is it closed under scalar multiplication? In other words, is it a subspace? You could conclude the answer to that question if you answered these two. So see about that. Come to office hours to discuss. Or you can email, certainly. You could even start a discussion post, maybe. I don't know. You don't have to do that. But you could. Okay. Let's look at this last example over here. Let's consider the system x1 plus x2 plus x3 plus 3x4 equals 0, x1 plus 2x2 plus 4x3 plus 5x4 equals 0, and finally x1 minus 2x3 plus x4 equals 0. Notice this is a homogeneous system, right? That's what we have when the right-hand sides of all the equations are all zeros. Now, I want to see how we can solve this with the help of a computer and get that this is the general solution. I claim that I've already done this and I found that this is our general solution. How can we show this before we do something with this system? Let's do this in Octave. We've seen how to use Octave or MATLAB to solve a system when there's a unique solution. This has more variables than it has equations. This will definitely have many solutions in that case. It's consistent and it's got more variables than equations. So let's take a look at how to do this on a computer. Let me share Octave with you. And to do this, I am going to set up an augmented matrix for my system. So taking this system, kind of running out of room, I'll write my augmented matrix down. 1, 1, 1, 3, 0, 1, 2, 4, 5, 0, and 1, 0, -2, 1, 0. So that's our augmented matrix. Let's pop that in here. I'll call this matrix A. A equals, open square brackets. First row is 1 space, 1 space, 1 space, 3 space, 0. Semicolon. Then sorry, you can see my fingers here. My webcam is incredibly low, so you're going to see a lot of my fingers. I'm in a bad place on my computer. Wow. All right, 1, 2, 4, 5, 0. Next row, 1, 0, 2, -2, 1 space 0. I want to see this matrix. I want to make sure Octave has interpreted this the way I expected. I'd recommend doing the same in MATLAB. This does look like the correct augmented matrix. Now, if I wanted to solve, we saw to solve when in the case that there's a unique solution, it's very easy just by using RREF. So let's do the same thing here. I take RREF of this guy. This is the matrix I'm left with. I'm going to write that here. The matrix I'm left with is finally all zeros across the bottom. So if you do this by hand using row operations, or if you do it with MATLAB or Octave, this is the RREF, reduced row echelon form. Of our augmented matrix. And from here, we can actually use this pretty easily to unpack back into equations and solve. So let's see how to do this. I will get away from Octave now. I don't think I need it anymore. Oops. What have I done? Let's fix this up. Okay, I think we're back in business. Here we go. So I've got my, oops, a little close. I've got my reduced row echelon form of this matrix. Again, let me carry out my workspace over here. If I unpack that again back into a system of equations, that system would read x1 minus 2x3 plus x4 equals 0. X2 plus 3x3 plus 2x4 equals 0. And the last equation would just read 0 equals 3. 0 equals 0, which is not a problem, right? 0 does equal 0. It just adds no new information to our system. No matter what we let our variables x1 through x4 equal, 0 will still equal 0. We will automatically have that last equation satisfied. So we drop it. It doesn't add any new requirements or information. We just drop it. And now we look at this reduced down system and we identify our leading variables. And any variables that aren't leading, right? Meaning that in reduced row echelon form, our lead variables are the first ones we see when moving across the equation left to right. X1 is the first variable here. x2 is the first variable we see here that doesn't have a 0 coefficient. So those are our leading variables, meaning the remaining variables are free. Now remember, the idea here is to solve for the leading variables in terms of the free variables. So x1, for example, is 2x3 minus x4. Just add that stuff to the other side. And x2 is negative 3x3 minus 2x4. Move that stuff over. Well, x3 is just itself, and x4 is just itself, right? That's what it means to be these free variables. They're not controlled or expressed in terms of the other ones. But remember, we didn't typically leave it like this. Typically, we replace the free variables with a parameter value. So I will let x3 be our R parameter and x4 equal an S parameter. So if I do that, then we have, this I'll consider my full solution here, x1, x2, x3, and x4 equal, let's see what I get. In the first component, x1 here is 2x3 minus x4, but I'm replacing x3 with an R and x4 with an S. So this is 2R minus S. The x2, the next component, is negative 3x3 minus 2x4. Again, replace those with R and S, and we get negative 3R minus 2S. Finally, x3 is just the R parameter, and x4 is the S parameter. So notice what's going on here. Notice this, first of all, is the same solution we came up with over here. This is the general solution. Plug in any value of R and S, any real number for R and S, and the x1, x2, x3 ordered quadruple you have is going to satisfy your system. You have infinitely many, right? So what I want to do now is see if we can show that this set of solutions, the set W of ordered quadruples, x1, 2, 3, and 4 in R4, such that the x1 equals 2R minus S, x2 equals negative 3R minus 2S, x4 equals R, and x3 equals R, and x4 equals S for some values of R and S. In fact, I'm not happy with this over here. Let me fix this up. Let's make this visible, huh? The set of all ordered quadruples in R4 such that x1 equals 2R minus S, x2 equals negative 3R minus 2S, x3 equals R, and x4 equals S for some real numbers R and S. That's the set W I'm really trying to describe. Starts all the way over here, ends all the way over here. Okay, but that's just the solution set. Of that homogeneous system we started with. So we're asking, is the solution set to this linear system, this homogeneous linear system, a subspace of R4? Well, how can we figure this out? Let's take a look. I want to make sure I don't do anything too different than the notes I'm providing, or in the notes I have written down. Yeah, let's take a look here. Assume you have, right, in order to see if this set W is really a subspace, right, is it a subspace of R4? We have to take two elements in W and see if, using those two elements, see if it's closed under addition. And we have to take a scalar multiple and see if it's closed under scalar multiplication. So let's see what we get here. Let's let U be in W. And let's write U as, right, it's got the U values have to have this form. I'll call it 2R1 minus S1, negative 3R1 minus 2S1, R1, S1. And take another vector, V in W, call it 2R2 minus S2, minus 3R2 minus 2S2, R2, S2. Right, the idea is we get a solution, we get something in W for any value of R and S we choose here. One element of W will be this vector where I've plugged in R1 and S1. I'm not saying what those R and S values are, I'm just saying this is one element. We'll label a different one by using different parameter values, R2 and S2 instead. So we have to add these together, and we'll see this comes together pretty quick. If we add these together, what do we have? Adding first components, that's what we have. Adding second components, and adding third components, and fourth. That's the sum. Now we're asking, is this still of this form? If it is, we better be able to write it in a way that really shows it does take this form, where the x1, x2, x3, and x4 have this relationship to each other in terms of R and S. Well, look what we can do. Right, this guy is 2 times R1 plus R2 minus S1 plus S2. That's the same as what I have here. It's just grouped in a sort of convenient way. In all this stuff, I'll group things similarly. Negative 3 R1 plus R2 minus 2 times S1 plus S2. Finally, R1 plus R2, S1 plus S2. And so the question is, when we added U and V, does the result come out to be of this form? X equals 2 times some number minus some other number. X2 equals negative 3 times that first number minus 2 times that second number. X3 is that first number and X4 is that second number. Is this of that form? Well, I claim it is. Let R equal R1 plus R2. Right, if R1 and R2 are real numbers, add them together, and the result that I'm calling just R, that's still real. And let S be S1 plus S2. Then we're seeing the sum here is of the right form. This is 2 times our R value minus our S value. 2 times some real number minus some other real number. In the next component, we have negative 3 times that same first of those real numbers, negative 3 times R, the first of those real numbers, minus 2 times S. And finally, out at the end here, R1 plus R2 is just R, S1 plus S2 is just S. So since these sums, R1 and R2, R1 plus R2 and S1 plus S2 are still just real numbers that I'm calling R and S, we can express this and see that, yeah, U plus V is still exactly of this form. This form required up here to be in W, since those values R and S that really came from R1 plus R2 and S1 plus S2 are still just some real numbers. So this is in W. It has the right form still. So this is closed under addition. Now I recommend that you go through and try to see if you can show that it's closed under scalar multiplication. See if you can work that out. Come to office hours certainly, or email if you have questions about it. It's a good exercise. Let's see if you can work that out and let me know, get in touch with your results there. Is it closed under scalar multiplication? Might take some doing to actually show that it is, but I claim it is. You can show this. It is closed under scalar multiplication. And so W is a subspace of R4. It's a subspace of R4 because it's closed under addition and scalar multiplication. And it turns out this isn't at all a coincidence. It turns out anytime you look at a linear system, a homogeneous linear system, zeros on this side, you will always end up with a solution set that forms a subspace in R4, for example, here, since you had 4 variables. If you had 3 variables, it'd be in R3. But this is what we really wanted to see. This is the big result that I will write somewhere. Don't know where. Yeah. Okay. Had a little technical difficulty there, but I think I've caught up with my computer's caught up with me now. Let's write this big result that we were mentioning. But this is no coincidence that the solution set of this homogeneous system formed a subspace. The solution set of any linear homogeneous system of equations forms a subspace. Okay, so that was the big result I wanted to end with. And this kind of makes sense with some of the intuition I mentioned before. When I mentioned that, where were we? Yeah, that when we talk about subspaces, we are really thinking of, a nice general way to think of these is as lines or planes that go through the origin. And since we've already seen that any homogeneous system has to have a trivial solution, this is the solution where all the variables equal 0, right? That's obvious to see that that will always solve a homogeneous system. Then we know that the origin is in that solution set. So the solution set for this homogeneous linear system will go through the origin. It's more of a leap to see why it's closed under addition and scalar multiplication directly. You got to go through some math for that, but at least maybe we see why it is pinned to the origin, because all the variables equaling 0, that would be like 0, 0, 0, 0, 0, 0, 0, 4 of them, since we have 4 variables. That corresponds to the solution at the origin. It will always solve the system if we have zeros on the right side. In this case, we're seeing we have more than that. We have many more solutions than just the origin. But it turns out we actually do, in this case that we just went through over here for this homogeneous system, the solution set is a plane, similar to what we had over here, going through the origin. You might be thinking, how can you tell it's a plane? The solution set has, it's a subspace, and it has 2 parameters, meaning it's a 2-dimensional set in 3-dimensional and 4th-dimensional space. 2-dimensional set of this particular type is a plane. Okay, so let's not forget a solution set of any linear homogeneous system of equations forms a subspace. All right, I think that's about all we can do in this section. More next time. Thanks for your attention.